Let's talk a bit about graphs with asymptotes. When sketching our curves, what do we know? We know curves will always bend towards the asymptote. We also saw that they will never cross a vertical one. Vertical ones are exclusion in the domain, so it can't touch them. However, it is possible to cut horizontal and oblique ones because that's telling us what happens out at the extremities. So when it's not out at the extremity, it's like the asymptote doesn't exist, so it can cut it if needed. When we're dealing with this sort of function, so a rational function, we've got some polynomial divided some other polynomial, we know we could do a polynomial division and rewrite it like so, a quotient plus the remainder over the divisor. Now when it's in that form, we can get a lot of information. The bottom of the fraction can't equal 0. That's how I can find the vertical asymptote, by just looking at the equation. But the quotient, that will be the horizontal or the oblique asymptote. And then if I look at the remainder, if it's possible for that remainder to equal 0, that's where it will cut the horizontal or oblique asymptote, if it does indeed cut it. Now with that information, I can now draw a nice curve. I've already factorised it. If I want to do my polynomial division, it actually would have been better if it was expanded out, I suppose. So x squared minus 1 into x squared plus x minus 6. If I did that division, okay, obviously it's going to go in once because the coefficients of x squared are the same. And we'll get a remainder of x minus 5. So I could rewrite that function in this format. And now let's draw out some information. Top of the fraction equals 0 when it's in factorised form. Well, that's going to give me the x-intercepts, because I would say, well, when is y equal to 0, that's going to be the top of the fraction equals 0. Okay, I know I've got x-intercepts at -3 and 2. Y-intercepts are always very easy to find, so substituting 0, that's 6. Now I look at the bottom of the fraction, I know I've got vertical asymptotes at plus or minus 1. So let's put those in. There's going to be a horizontal asymptote at y equals 1. I'll now put that in. And if I look at the remainder, x minus 5, it is possible for that to equal 0. So I know it's going to cut the horizontal asymptote over here at 5, 1. Now that is enough information to draw a sketch. In the first section, moving left to right, it must do this because it has to go through that x-intercept. I know it doesn't cut the horizontal asymptote because we said the only place it does over here. And I also know it has to bend towards the vertical asymptote. So it's got some sort of hyperbolic shape over on the left-hand side. If we look at the middle, well, it goes through 6 and it's got to bend towards these asymptotes. But I know it's not going to cut the horizontal one, therefore the only thing it could do would be something like that, sort of U-shape. Now I go to the right-hand side, and this one's a little bit more interesting. I've got to go through the 2. I've also got to go through here. But then it won't cut it again. Pardon me for the dodginess of this curve, but it's very hard in PowerPoint to draw a nice smooth curve. Something like that. What it basically will do is, yes, we know we've got the vertical asymptote here, so it's bending towards it. It's going to come through 2. It's going to pass through 5, but it's got to come back down to bend towards the asymptote. So it'll keep going up and turn at some point. That's like very dodgy the way I've drawn it, but it would have to go up and then come back down and towards that horizontal asymptote. Okay, what about this one then? I've got a cubic on a quadratic. Okay, well, let's do the division on that one. And it looks like x minus 1 and a remainder of 4x minus 4. Could be rewritten that way. Okay, let's get the information out of it. X-intercepts, if I look at the top of the fraction of the original question I was given, it's going to be minus 1, 1 and 2. Y-intercepts, substitute in 0, minus a third. Vertical asymptotes, -2 and 3. Oblique asymptote this time. It's going to be the line y equals x minus 1. Put that one in. And yes, it does cut, because 4x minus 4, that would be when x equals 1, but mind you, we already knew that one because we'd drawn it in and it was passing through our x-intercept anyway. But that's the only time it's going to cut that. So what does this picture look like? Okay, again, working left to right. I've got to be trapped in this little triangle down the bottom here because I don't have an x-intercept on the left-hand side of that asymptote. So I know it's going to do something like that. Now, the next piece. I've got to go through minus 1. I've got to go through the y-intercept of minus a third. I know it's going to cut at 1. It's also going to go through 2. And it's going to go towards these asymptotes. It'll do something like that. And that brings us to the right-hand side. Again, we've got a situation where it's going to be trapped inside that triangle there. That would be a rough sketch of that curve. But let's look at reciprocal functions in general. If we want to draw the reciprocal of any graph, so 1 over function x, how can we do it? Well, we draw function x first. We use that as our working, if you like, and then draw out some key things. So when the original function, the one we're turning upside down, is equal to 0, then the new one must be undefined, because we'll end up with 1 on 0. In other words, vertical asymptotes are going to exist there. Here's a random function where I try to put all sorts of features in there. I've got a horizontal asymptote, I've got turning points, I've got all sorts of things there. But what I'm saying is these 3 x-intercepts will become vertical asymptotes in this new graph we're going to create. The reverse would also be true. If in the original graph the function's going towards infinity, then my new graph must be going towards 0. In other words, those asymptotes will become x-intercepts sort of. So there's going to be an x-intercept sort of. You see, because what we're drawing is a composite function. It's like if I said to you, draw this curve, y equals x over x, which you would think, oh, that's just y equals 1. I'll just draw a horizontal line. But it's not. If you were to draw that, it certainly looks like that, but I would have a point of discontinuity right there. Because to substitute into that function, what do you get? You get 0 over 0. What is 0 over 0? Undefined. That point is actually undefined. Why? Because we're going to be substituting into 1 on function x, and function x was undefined. Okay. Now, other ones, remember we're turning every y value upside down. So knowing where 1 is becomes very important, because if you turn 1 upside down, you get 1. I know those points will stay in the same position. They're not going to change. The same would be true for negative 1. Turn negative 1 upside down, you get negative 1. I'm assuming that turning point there is negative 1. The horizontal asymptote here, again, I'm turning it upside down. It was a value that's below 1. Therefore, when I turn it upside down, it becomes a value bigger than 1. So I've moved it up bigger than 1. If the original graph is increasing, then the reciprocal graph will be decreasing, and vice versa. If the original graph is positive, the new graph will still be positive. Turning a positive number upside down doesn't change its sign. Negative will stay as negative as well. That now helps me work out where this new graph is going to travel. I've just shaded in the sections that I now know it's going to travel. Okay? Working from left to right. Original graph is below 1, therefore the new graph will be above 1, but it can't go past that horizontal asymptote because this curve didn't go past the horizontal asymptote. So it must be in that little section there. Now I'll go in the next section, and the original graph is above. The original one was just above, so my new one is below, but it's going to stay positive. It can't all of a sudden turn into negative. The next little section, and I'm just talking about the magnitude here rather than the sign, but original graph was greater than 1, it becomes less than 1 becomes greater than 1, and so on and so on and so on. I'm just doing that for each particular section. I now know roughly where it travels. When we differentiate, and okay, we haven't looked at calculus yet, but if I was to differentiate 1 on function x, I end up with minus the derivative on the function squared. So that therefore means stationary points which occur when the derivative is equal to 0. So in my new function, the derivative is still going to be 0, because the original derivative was 0. I've got 0 over the function squared. What that basically is telling me is stationary points at those x values will still be a stationary point. What that means is this turning point up here, where it turns, the curve will still turn. Its value, however, is going to change. It was a number bigger than 1, and it therefore becomes smaller than 1. And over here, well, it's still 1. There it is. That would be our reciprocal graph, using all those rules. Got to bend towards asymptotes, pass through those particular points, and so on. Let's just, there we go. There's a better picture of us. So that's how we can draw reciprocal graphs. Okay.